Bioreactor designed for chemical engineers. Um, Regardless of whether the process is aerobic or anaerobic, it generally involves several steps before it reaches the production fermenter. The first step is cultivation of the organism in the lab. That is often done in shaker flask under the direct supervision of microbiologists. A portion of high cell density broth is then transferred from the shaker flask to a seed tank, which is a which is a small fermenter designed to increase the quantity of organism. From there, it is usually transferred to a large fermenter called the inoculum tank. Finally, the contents of the inoculum tank are transferred to the production fermenter. The conditions in the shaker flask, seed tank, and inoculum tank are optimized for the production of more bugs. Mass transfer. Although not a major factor in anaerobic fermentation, mass transfer is crucial in aerobic fermentation. Without sufficient transfer of oxygen from the air to the liquid, organism may go into shock or make the wrong product. Aerobic processes demand a certain oxygen uptake rate under steady state conditions. This equals the oxygen transfer rate. Although our the term in parentheses is the driving force. It can be expressed in a simple form or in a log mean form in a small vessels where both liquid concentration and saturation are almost constant. The simple form is adequate. Fucking bitch. It might be tempting to increase the saturation value by increasing the back pressure. However, there is a limit to how high back pressure can be raised. The first bioreactors used multiple Rushton turbines, which create a stage mixing pattern that doesn't promote oxygen or nutrients uniformity. Almost all new fermenters have a combination of axial and radial impellers or all axial impellers to improve mixing. When nutrients or dissolved oxygen are not uniformly distributed, productivity, yield, and product distribution can be affected. Some processes and organisms are more sensitive than others. Unfortunately, there is presently no good way to model the actual concentration distribution in a fermenter. Various researchers are attempting to use numerical methods to combine mixing, mass transfer, and reaction kinetics to plot dissolved oxygen distribution, but it is a very complex process and there are no models on the market to do this in a user-friendly manner. There are, however, several strategies to improve mixing in a fermentator at a given ODR. Use a combination of axial and radial impellers with optimal power distribution. Heat transfer requirements for bioreactor vary. Anaerobic fermenters and cell cultures reactors typically have very low rates of heat production, whereas aerobic fermenter can have quite high heat production rates. The rate usually correlates well to oxygen consumption. A good estimate is 460,000 kilojoules per mole of oxygen consumed. Agitation equipment should be chosen based on mixing and mass transfer requirements, not on heat transfer. The exponent on agitator power input on the process side coefficient is only about 0.22, which can be derived from the above equations and agitator power proportion. In low viscosity fermentation, sometimes the heat transfer resistance on the cooling media side of the heat exchanger system is high than on the agitated side. In such cases, the overall heat transfer coefficient may be improved by using internally finned pipe or tubing or an annular double pipe arrangement. If the vessel is jacketed, a dimpled jacket or a half pipe jacket may be more effective than a plain jacket. Process optimization. There are many opportunities for chemical engineers to optimize bioreactor design. Vessel aspect ratio in aerobic fermentation, tall thin vessels have a higher absolute pressure at the bottom, which provides a higher mass transfer driving force. They also have a higher superficial gas velocity for a given airflow rate. The overall result is that they may require less total power for a given OTR. In addition, they are easier to equip with sufficient heat transfer surface area. There's no simple rule of thumb to determine the optimum aspect ratio. Optimization consists of performing fairly detailed calculations for a series of aspect ratio to determine the pre- lowest present worth of capital and operating costs for design that are technically feasible. Working with CFD providers to fine-tune the design, although there are no user-friendly codes on the market to predict such things as DO and nutrient dissolved oxygen and nutrient profiles, computational fluid dynamics experts should be able to model these by combining mixing mass transfer and oxygen consumption models. This work is expensive. Plan to spend at least 100,000 for 2 or 3 simulations of the semifinal design, but this may be money well spent if it avoids yield or productivity problem by detecting low DO areas. For relatively insensitive fermentation, it may not be worth the time and expense.